This skill module covers qualitative phase behavior and vapor-liquid equilibrium at the core knowledge level. This section discusses why this topic is important. Many production processing operations involve control of the phases present. Selected components must be vaporized or condensed to achieve specified goals. For a given mixture's fluid composition, the phase envelope defines the vapor, liquid, and two-phase regions. Determination of the bubble and dew point curves fixes the extent of the two-phase region. Within the two-phase region, it is necessary to predict vapor-liquid ratio and the composition of both phases. The latter involves the concept of equilibrium. Equilibrium is commonly used to describe a state wherein the progression of time has no effect on system behavior. In a phase behavior context, the composition of the vapor and liquid in contact will remain constant with time. It takes time to reach equilibrium. In a typical hydrocarbon system, up to several minutes of contact is required. Since the fluids are often intimately mixed in the piping upstream of the separator, it is usually assumed that a separator should be treated as an equilibrium process. In absorption and fractionation calculations, no true equilibrium exists because the vapor and liquid are not in contact for a sufficient period. The assumption of equilibrium, made for convenience, must be corrected by an efficiency factor. Accurate knowledge of phase behavior is essential to the design and operation of processing facilities. The cost of obtaining good data is usually trivial compared to the economic benefits obtained. For facilities work and equipment troubleshooting, it is important to understand where the process is operating relative to the phase envelopes. Often, this can help determine the cause of a problem or how to avoid the problem in the first place. In facilities operations, the understanding of where the process is on a phase diagram can often help the engineer and operator avoid extremely embarrassing design and operating mistakes. The oil and gas industry is full of many war stories about phase diagram disasters. Most instances are never related back to the phase diagram misunderstanding. In one well-documented but poorly published case, a dry gas pipeline that was pigged flooded miles of sandy beach. In another case, thousands of kilowatts of compression power were installed to maintain the pressure of a reservoir above the dew point, when in fact the reservoir was at a temperature above the cricondentherm. In many cases, equipment manufacturers and purchasers of gas have specifications of superheat or dew point that have not been met and led to upset customers and/or millions of dollars of lawsuits. Understanding pure component phase behavior is important in understanding processes that either produce or use pure components, such as fractionation, NGL product storage, and propane refrigeration. Understanding how to apply pure component vapor pressure curves to propane refrigeration system performance can help one understand the process operating conditions inside of the propane refrigeration loop. Understanding multi-component phase behavior is important in understanding how the fluids behave in our processing facilities. Being able to predict phase conditions for a fluid composition allows one to look inside the pipe and confirm if the fluid is in the superheated vapor phase, dew point, two-phase, bubble point, or subcooled liquid phase. Understanding the phase condition is the first step in troubleshooting equipment and facilities. Characterization of the C6 plus heavy end fraction of a natural gas stream is not routine. This is often where we get the data and analysis wrong due to the challenges of getting representative samples of the reservoir fluids, the fluid recombination, and laboratory analysis to determine the true boiling point analysis of the small heavy end fraction. This module is important because it discusses what can go wrong in the facility design and operation if the heavy end characterization of the inlet well fluids is not correct. Hydrocarbons are frequently produced with non-hydrocarbon impurities. Understanding how impurities such as carbon dioxide, hydrogen sulfide, and nitrogen impact the phase envelope is important. Carbon dioxide and nitrogen can be injected into the reservoir for either enhanced oil recovery or for gas cap pressure maintenance. Understanding the phase behavior is key to understanding how these fluids can be utilized downhole to increase production. Understanding applications of phase envelope is important because phase envelope is an excellent tool for facilities design, operation, and troubleshooting. For a gas mixture, two process paths of A to B and C to D are shown in the figure. Liquids are formed at points B and D. The phase envelope guides us to the mechanism and amount of liquid formation to apply the appropriate solution. Understanding the phase behavior is a useful tool in troubleshooting equipment and facilities. Performing VLE calculations are important for determining the liquid L and vapor V rates leaving the separator, as well as the stream compositions XI and YI, the fraction of liquid and vapor in the mixture, LPG tank pressure at known temperature, gas pipeline temperature at known pressure, etc. Flash stabilization is the most common method of stabilizing crude oil. Condensate can be stabilized this way as well, but stabilizer columns are more commonly used in condensate systems. Several stages of separation are often used as shown in this figure. This system is classified as either two-stage or three-stage separation, depending on whether the stock tank is considered a stage. If gas is flashed off of the stock tank, it is a separation stage. If the crude oil meets the vapor pressure specification when it leaves the separator immediately upstream of the stock tank, then the tank is not considered a separation stage. The number of separation stages can vary from 1 to 5, depending on the flowing tubing pressure and the vapor pressure specification. The read vapor pressure RVP and/or true vapor pressure TVP are important specifications for safe handling, storage, and transportation of crude oils and liquid products. The RVP or TVP specifications are achieved by utilizing flash or column stabilization. This skill module discusses the topics shown here. You may also be interested in these gas conditioning and processing principles skill modules.